So in section 12.4, we're going to be looking at what's called the cross product of two vectors. And basically the cross product is going to become useful to allow us to find angles between vectors, or also to determine when vectors are perpendicular. So let's take a look at a little of that here. Consider putting two vectors u and v with their tails at the origin, and consider their component form, x1, y1, x2, y2. If we look at that, we know that these two vectors will be perpendicular, and another fancy word they're going to give you for perpendicular is orthogonal. Two vectors would be orthogonal if the slopes of the lines containing the vectors are negative reciprocals of each other. So what's my slope of the line containing u? The slope is going to be y1 over x1, and the slope of the line containing vector v is going to be y2 over x2, so that would be y2 over x2, and those vectors are perpendicular if and only if that product is negative 1. Go ahead and cross multiply, and then you will get y1 y2 equals negative x1 x2. Go ahead and then set one side equal to 0. You can get x1 x2 plus y1 y2 equals 0. So if this product of, taking my components from component form of the vector, if x1 x2 plus y1 y2 equals 0, then my vectors will be perpendicular. This value here, this value right here, x1 x2, x1 times x2 plus y1 times y2, is called the dot product of two vectors, and that can be again written as v1, or sorry, it'll be u dot v equals, and again we had here x1 x2 times x2 plus y1 times y2. And we know then that when the dot product equals 0, our vectors are perpendicular. There are some properties of the dot product which are easily verified writing stuff in component form, and that might show up in the homework, or there'll be some examples. You might want to just think it through yourself. We'll look at one of these cases. Prove that u dot u, or the dot product of u with itself, is the magnitude of u squared. So let u equal x1 y1, so we can put u here with its tail at the origin, and in component form let it be x1 y1, x1 here, y1 here, and then go ahead and look at your u dot u. So u dot u is going to be x1 x1 plus y1 y1, which equals x1 squared plus y1 squared. Well, what's the magnitude of u going to be? Well, looking back up here, our magnitude of u, our length of u, is going to be the square root of x1 squared plus y1 squared. So therefore, the magnitude of u, quantity squared, is going to equal the square root of x1 squared plus y1 squared, quantity squared, which equals x1 squared plus y1 squared, and that indeed is our dot product of u with itself. So suppose I want to look at where u minus v, vector u minus v, is relative to two vectors u here and v here. If I got my u and I want to add negative v to it, I want to go in the opposite direction and have the same magnitude, and I want to do my head to tail method. So I'm going to put negative v is going to go down in this way, so slide that over. It's then going to go down in this way. So then my u plus negative v is going to yield this vector right here. It's going to yield me that vector right there. Now if I look at this figure for a minute, these two sides are going to be parallel and congruent because they're vectors of the same magnitude in the opposite direction, which means this whole figure here is a parallelogram, and which means then if I go ahead and draw this vector in up here, this vector is going to be parallel to and equal in magnitude to this vector down here. So this vector up here actually, from my original diagram, here's u, here's v, and up here forming this triangle is then going to be u minus v. So again, in summary, I've got two vectors. Here's a u, here's a v. U minus v is going to be this vector right here, forming this triangle, forms a triangle. So why did we look at that situation? Well, we looked at that situation because what we're going to be interested in doing is if I put two vectors here whose tails here are at the origin, let's say like this, and call them u and v, I'm going to be interested in finding the angle in between them. And provided that angle is between 0 and 180 degrees, we're going to be able to do that. The work we just did, we saw that our vector here is going to be vector u minus vector v, and we see a triangle, and we want to find an angle knowing three sides of a triangle, because remember, I can find the magnitude of u, the magnitude of v, and the magnitude of u minus v. If I can find those things, I've got an angle here. The law of cosines perhaps could come into play to allow me to find that angle here. So let's see how we do that. Let's look at giving coordinate form to our vectors. We'll let u be the vector x1, y1. We'll let v be the vector x2, y2. And therefore my u minus v from our previous work is going to be x1 minus x2, y1 minus y2. The magnitude of u is going to be x1 squared plus y1 squared square rooted. Magnitude of v, similarly x2 squared plus y2 squared, and similarly our magnitude of u minus v is going to be x1 minus x2 squared plus y1 minus y2 squared. So looking at our law of cosines, we've got this triangle. We know that opposite theta, the length of that side, which is going to be the magnitude of this vector, the magnitude of u minus v squared, equals the length of this side, which is the magnitude of u squared, plus the magnitude of v squared, minus 2 magnitude of u, magnitude of v, times cosine of that angle. And I want to solve this now for cosine of theta. So if you get cosine of theta alone, or you can go ahead and just, let's get cosine theta alone here. I'm going to move this mess all the way over to the other side and move this over to this side, so I get 2 cosine, let's back up on that. I get 2 magnitude of u, magnitude of v, cosine theta, equals magnitude of u squared plus magnitude of v squared minus magnitude of u minus v quantity squared. If I then go ahead and divide both sides by 2 magnitude of u times v, I get cosine theta equals magnitude of u squared plus magnitude of v squared minus magnitude of u minus v quantity squared all over 2 magnitude of u magnitude of v. And that looks like a fairly messy formula, and it is a fairly messy formula, and we're hoping that something's going to simplify. And actually the bottom looks pretty clean. 2 magnitude of u times magnitude of v, that looks fairly clean. Let's see what we can do with this top by thinking back of what on the previous slide we got these values equal to. So leaving the denominator alone here is 2 times the magnitude of u times v. This big mess up top here, if I go ahead and plug in our component form for these three terms, and you can see how that's done on page 442 in your text. If you go ahead and plug those component forms in, a lot of things will cancel, getting you down to x1, x2 plus y1, y2 for all this huge mess up top. And we recognize that as our dot product of u dot v. So we do have a formula then for the cosine of the angle between two vectors. If the vectors' tails are located at the origin and that angle is between 0 and 180, the cosine of that angle is equal to the dot product in the numerator, u dot v, over the denominator, 2 times the magnitude of the two vectors, the product of the magnitude of the two vectors. This section also talks about vectors being parallel, and they also talk about the zero vector, and they mention a couple things. They mention vectors are parallel if, for example, you have some vector v2 equals some scalar multiple, say v1 is some scalar multiple of v2, then those two vectors will be parallel. Now they could be, you can move vectors around, so you could have parallel vectors, say, located in two different places in the plane, or maybe, one is on top of the other. That certainly, they could be two vectors. We'll consider those to be parallel vectors because we can move vectors around. The section's also going to talk about the zero vector, and they're going to say that the zero vector is parallel and perpendicular to all vectors, and my zero vector, the letter 0 with a vector symbol over it, or they use, they'll call the zero vector in your text, they'll just write out the words zero vector, but I'm going to call it 0 with a vector symbol over it. It is parallel and perpendicular to all vectors. And finally, they're going to talk about the fact that if you look at the dot product of u dot v, since I'm multiplying x1, x2 plus y1, y2, those are numbers, this quantity is a scalar quantity. It does not have direction. It's simply a number. It's called a scalar product. It's a scalar quantity. So a dot product is a scalar quantity. It's a number.